Okay, good morning. In today's session, I will be discussing some examples on shear force and bending moment diagrams for various loading conditions on overhanging beams as well as simply supported beams. So already we have discussed in previous lectures some more examples. Some examples already we have discussed in previous lectures. In today's session, we will be discussing some more examples on overhanging and simply supported beams. So let us first consider the example shown in figure. An overhanging beam subjected to various loads. Here the loads consist of UDL point load, partial UDLs and point loads it consists. So here the span of the beam between supports is 8 meters and overhanging portion is 2 meters. So total length of beam is 10 meters. So as a first step, we will find the reactions at supports. Okay. The very first thing to do is to find the reactions at the supports A and E, RA and RE. So for that, we'll consider the moments about A or E. That means apply the condition sigma MA equal to 0, one of the equilibrium conditions. So this eliminates RA and we will have RE in the equation. Okay. So now the moments of forces including reaction at E are written here. So RE into 8 is equal to, this is anti-clockwise, that is equal to sum of clockwise moments. So all the applied loads produce clockwise moments. So 10 into 2 into 1, that is due to part UDL acting on AB. Next, point load 20, moment is 20 into 2. Next, second point load here, again 20 kilonewtons and its distance is 2 plus 3, 5. Plus third point load 10 into, distance is 2 plus 3 plus 2, 7, plus fourth point load here 40 kilonewtons acting at free end and its distance is 10 meters. Okay. So the reaction RE is, this is 20 plus 40 plus 100, that is 160 plus 70, 230 plus 400, 630 divided by 8. 630 divided by 8. So it comes out to be 78.7 kilonewtons. 78.7 kilonewtons. That is the reaction at E. Now, how will you get the reaction at A? we know the condition RA plus RE equal to total downward load. It means the condition sigma Fy equal to 0 gives RA plus RE equal to total downward load. What is the total downward load? 10 into 2, 20 plus 20, 40 plus 20, 60 plus 10, 70, and there is one more UDL. This is 20 kilonewton per meter. That we have not considered here. Let us consider that also. 20 into length is 3 and distance is 5 plus 1.5, 6.5. Okay, 5 plus 1.5, 6.5. So this gives load 630 plus 20 into 6.5. That is 65 into 6. So 65 into 6 is 390 plus 630. Up to here it is 630 plus this is 390. So it is 1020 divided by 8. Okay. So 115 kilonewtons. RE is 115 kilonewtons. So what is RE now? Total downward load is 10 plus 20, 20 plus 20, 40, 60 plus 10, 70 plus 20 into 3, 60. 70 plus 60, 130 plus 40, 170 minus 115. So total downward load is 170. Therefore, RA is 170 minus 115. That is 55 kilonewtons. RA is 55 kilonewtons. So knowing the reactions, what we'll do to draw the shear force diagram, we consider various sections. For every load change, we consider one section. Okay, section X. Say. You can take origin either from A or from B or from E, other support. Okay, let us consider this origin from A only. Okay, to find shear force, let us consider origin of this section at A. So what is the shear force at A now? RA minus 10 into X. RA minus this length of UDL is 10 into X. Okay, that is applicable between A and B only. That means for the limits of X from 0 to 2. Okay. Again, from B to C, you need to consider next section. Okay. Actually, here between B and C, shear force remains same because there is no load. Shear force will be constant between B and C, but bending moment changes. Bending moment changes. Okay. So like this, first you consider the section in AB. Okay. Let this section is X1 with origin taken at A. So consider section 1 between A and B with origin at A. Origin at A. So what is the shear force at A? RA minus 10x. And what is the bending moment at A? at x. RA into x minus 10x into x by 2. That is 5x square. 55x minus 5x square. Okay? 55x minus 5x square. So, the limits for x here 0 to 2. Between A and B only these equations are valid for shear force and bending moment. Now substituting x 0, you will get shear force at A as 55. Okay? I'm not discussing here about the convention, sign convention for shear force and bending moment, because in previous lectures we have already discussed the sign convention. Okay? Left side upwards is positive for shear force, right side downwards is positive, and vice versa. Okay? So substituting 0 here for x, you will get shear force 55 at A. And what is the bending moment at A? In this substituting x0, bending moment will be 0. That means the bending moment at simply supported end will be 0. Similarly, at x equal to 2, that means when the section is at B, so substituting 2 here, you will have 55 minus 10 into 2, 20, that is 35 kilonewtons. And bending moment, this is shear force. Okay, there is shear force at B, and coming to bending moment, substituting 2 here, 55 into 2 minus 5 into 2 square, so 110 minus 20, that is 90 kilonewton. And what is the variation here of bending moment? Shear force varies linearly, bending moment parabolic variation. Variation of bending moment is parabolic. Okay, that is clear from this equation. Okay, similarly, consider second section x2 between B and C. So for this section, take origin from A only, that means x from A. What will be the limits of x now? Between B and C we are considering this section. So x will be starting from 2, because from B to C it has to vary, isn't it? The section has to move from B to C. So when the section is at B, what is x? It is 2. And when the section is at C, what is x? 5. So 2 to 5 are the limits for x between B and C. Okay? And what is the equation for shear force now? RA into x minus 10 into 2, 20 into x minus 1. The distance from section x2. Distance of this resultant of UDL from x2 is x minus 1. Okay? And minus 20 into x minus 2, this distance. Okay? So, considering section between BC, the limits are from 2 to 5. The limits for x are from 2 to 5. So, between BC with limits from 2 to 5, what is the shear force equation? Shear force equation 55 RA minus 10 into 2, 20 minus 20 point load. So you consider here RA minus 10 into 2 minus 20. Okay? Understand? And what will be this resultant value? What is the result of this? 55 minus 40, that is 15 kilonewtons is the shear force. And this is positive. Okay? If you observe here, the shear force is independent of x. Shear force is independent of x. What does that mean? It remains constant between B and C. As x varies from 2 to 5, shear force remains same because it is independent of position of section. And this is because there is no load between B and C. Next, what is the bending moment at x? RA into x, 55x, minus 10 into 2, UDL, into x minus 1, minus 20 into x minus 2. Okay? Sorry, 10 into x minus 1 is distance, that is only load, into moment we want, the moment of this. What is the moment of this? 10 into 2, 20 into x minus 1. 20 into x minus 1. Okay? Minus 20 into x minus 2. That is for point load. And VR RA into x. Okay? So RA into x minus 10 into 2, 20 into its distance x minus 1. Next point load 20 into its distance x minus 2. Okay? So here if you observe, the bending moment varies linearly between B and C. So it is straight line variation. Okay? That is clear from this. So shear force is constant. Constant means it is parallel to the axis. Okay? Parallel to the axis. There is no variation. At B and C, it remains 15 kilonewtons only. So it is parallel to axis. And coming to bending moment, at x equal to 2, bending moment at B is, so when x equal to 2, this term becomes 0, and 110, 55 into 2 minus 20 into 2 minus 1, 20. That is 90. Okay? Units are kilonewton meters. Next, at x equal to 5, bending moment at C will be 55 into 5 minus 20 into 5 minus 1, okay, minus 20 into 5 minus 2. In this equation, we have to substitute 5 for x. So what will you get here? 275 minus 80 minus 60. So 140. 275 minus 140. So what will be the result? 275 minus 140 is 135 kilonewton meters. So the bending moment varies from 90 to 135. Okay? And variation will be linear. Understand? Next, consider third section. We have to consider third section. Between C and D we have to consider, because there is a variation of load, change of load here. point load is there at D. Okay. So consider the section between C and D. Third section, X3. Origin. Yeah, where to consider origin for this? You can consider origin either from A or from F or from E. Anything you can do. Let us consider the origin for this from E. Okay. Origin for this section X3 is from E. The right hand side we are considering now. So what will be the shear force considering right hand side? So the convention is right side downwards is positive, isn't it? So the value of RE is 115. RE is 115. So 40 is downwards, right side, positive. 10 is also positive. So 40 plus 10, 50 positive minus 115. Okay. This is about this point loads, including reaction. And how about UDL? It is downwards and on the right side. So it is positive. And its magnitude is 20 into x. Magnitude is 20 into x. The total UDL over length of x is 20 into x. Okay. So write the equation now for shear force between C and D. The limits. How about the limits? Limits are from 1 to 3. Limits are from 1 to 3. How it comes, we'll see. So what is the shear force at x? 10 plus 40 plus 20x. All these are downwards, right side. Okay. And hence it is positive minus RE 115. So it comes out to be 20x minus 65. 20x minus 65. Okay. Yeah. Now let us see the limits. So we are considering origin from E, isn't it? But the section moves between C and D. Okay. The equation is valid between C and D. So at D the value of x is 1. At C the value of x is 3. So the limits are from 1 to 3. Similarly, write the bending moment equation. What is the bending moment equation? Yeah. Bending moment, sagging positive and hogging negative. This is the convention, is it? So 115 into x. This is positive sagging moment. And due to these loads, it is negative hogging. Okay. So 115 into x. And how about this 40 into x plus 2? Distance of this is x plus 2. Okay. 40 into x plus 2 plus 10 into x minus 1. 10 into x minus this load. And due to UDL 20 into x by 2. Okay. All these are minus, negative. Due to loads, the moment is negative. Due to reaction, the moment is positive. So let us consider here bending moment at x. 115x minus 40 into x plus 2 minus 10 into x minus 1 minus 20 into x by 2. That is due to UDL, okay, of length x. It is clear? Now substituting the values. x equal to 0. That means x equal to 1. The limits are from 1. So when x equal to 1, the section will be at D. So shear force at D is, what is the shear force at D? 20 into 1 minus 65. That means minus 45 is the shear force at D. And coming to bending moment, when x equal to 1, this term will be 0. Okay. And 115 into 1 minus 40 into 1 plus 2. 40 into 1 plus 2. Third term is 0. So this is 115 minus 120. So minus 5 kilonewton meters. Bending moment at C, D is minus 5 kilonewton meters. Okay. Next, at x equal to 3. Okay. What is the shear force at C? At x equal to 3 means the section will be at C. So 20 into 3 minus 65. 20 into 3 minus 65. So that is minus 5 kilonewtons. And bending moment at C is, what is the bending moment at C? At x equal to 3. So 115 into 3 minus 40 into 3 plus 2 minus 10 into 3 minus 1. Okay. This is the equation. Small mistake here. We have not considered this. So 10x square also we need to consider, minus 10x square. Okay. This we have not considered in the previous. So 10x square. When x equal to 1, minus 10. So it is minus 15 will be. Okay. Similarly here, for x equal to 3, 10 into 3 square. 10 into 3 square. That also we have to consider. So total bending moment at C is 115 into 3 minus 115 into 3 minus 40 into 3 plus 2. 40 into 3 plus 2 minus 10 into 3 minus 1 minus 10 into 3 minus 1 minus 10x square 3 square. So it is 345 minus 5 into 40 200 minus 20 minus 9. Okay. So 345 minus this is 310. So it is 35 kilonewton meters. Bending moment at C is 35 kilonewton meters. Okay. Third section is over. Next, fourth section. We have to consider fourth section between D and E. Between D and E, origin is again from E only. Okay. So what will be the limits for x? The limits for x now. The limits for x will be 0 to 1 because section moves from E to D. So limits will be from 0 to 1. Okay. So consider section in portion DE. In portion DE. So shear force at x is equal to RE minus 40 minus 10 into x. Okay. So the loads we have to the right of section is RE, this 40 load, and this length of UDL. Three loads we have, including reaction. Okay. Similarly, bending moment. So this is 60, 75 minus 10x, and bending moment at x is equal to 115x minus 40 into x plus 2 minus 10 into x by 2. Okay. Yeah. Now the limits are 0 to 1. So substituting x equal to 0, you will get shear force at E, okay, as 115 minus 40, 75, okay, from this equation. And bending moment at E is equal to, this is 0, this is also 0, and 40 into x plus 2, isn't it? 0 plus 2 minus 60. So it is negative. Similarly, at x equal to 1, shear force at D is 75 minus 10 into 1. That is 65 kilonewtons positive. Next, bending moment at D. At x equal to 1, bending moment at D is from this 115 into 1 minus 40 into 1 plus 2 minus 5 into 1 square. Okay. So we will get 115 minus 120 minus 5. That is minus 10 kilonewton. There is one more section we need to consider between D and E and F. Okay, between E and F, we need to consider one more section. For that, we have only one load. Okay, so shear force is 40, right side of this, and bending moment is minus 40 into x. For this, we take origin at F, varies from 0 to 2. X varies from 0 to 2. Okay, so 40 is the shear force which remains constant between E and F, and bending moment varies linearly because bending moment is 40 into x, that is minus 40x, which is linear variation. So x0, bending moment at F is 0. So for section x5 between E and F, shear force at F is equal to 40 and shear force at E is equal to 40. Bending moment at F is 0 and bending moment at E is 40 into 80 minus, okay, minus 80 kilonewton. You can plot this values. You can plot all these values. Okay, by plotting these values, we will be getting the shear force and bending moment diagrams. First, let us see this loading diagram. So loading diagram is this, 20 kilonewton per meter, and point loads are 20, the radial is 10 kilonewton per meter, and this is 10, this is 20. Okay. So shear force diagram. Shear force diagram here at F it is 40, at E also it is 40, because there is no load, it remains same. At E we have a point load, that is the reaction upwards, so there will be a sudden change here to a value of 75 plus 70. So this is positive actually. This shear force is positive. Let us take it upwards. This is also positive. And at E, there is a sudden change because of the reaction. So shear force changes from plus 40 to minus 75. Okay. Now coming to this reaction at A is, this is 115. Reaction at A is 55, isn't it? 55. So it is negative. Left side of course is negative. So we'll take it below. And what is the shear force at B? 55 minus plus 10 into this length is 2. 10 into 2, 20. It is minus 35. Okay. So it varies from 55 to minus 35. And when you consider the section here, it is positive shear force. Sorry. Here it is positive, isn't it? Shear force due to this left side upwards, isn't it? Positive, our convention. So 55 will be taken above, and there is a decrease here in shear force from A to B, 35. Okay. Again, there is sudden change here by 20 because of this point. Okay. So what will be the remaining? 50. Okay. And which remains constant from B to C, because there is no load here between B and C. And there is again a sudden change in shear force. Okay. So plus 15 to minus 5. Okay. Yes. Plus 15 to minus 5. Next, between C and D, it is 2 meters. So shear force changes to 45 actually, 40, and this is already 5 here. So it is 45. And there will be a sudden change here. Okay. By 10. That means 45, and this is 55 to 70. Understand? Wherever there is a point load, there will be a sudden drop or rise in the value of shear force. Okay? Whenever there is a point load, including reaction, there will be a sudden change in the drop or rise. It may be increase or decrease, okay, in the value of shear force. So this is the shear force diagram. Similarly, you can draw the bending moment diagram. So bending moment 0 at F and at E 40 into this distance 20, 80. And what you need to remember, at overhanging end, the bending moment will be negative. Okay? Because it will be hogging. The shape will be hogging, isn't it? It bends downwards. So you will have negative bending moment. Okay? 80. And at A also it is 0. Bending moment is 0. So we have calculated the bending moments at various points. Okay. So let us see one by one here. Between A we have say. So bending moment at B is 90. Okay. Bending moment at B is 90. Next, bending moment at C is 135. Bending moment at D is negative, minus 15. Okay. So bending moment at B is 90. How will you get 90? 55 into 2, 110, minus 10 into 2, 20 into 1. Okay. So it is plus 90. And how about the variation? It is parabola because you have UDL. Okay. And coming to C, bending moment at C is 55 into 5. Already you have calculated it, 135 you are getting, is it? And its variation is linear between B and C, 135. Okay. Bending moment at C is 135. Next, between C and D, what is the bending moment at D? Bending moment at D is minus 10 and bending moment at C. Bending moment at C is 135. At C equal to 1, we will be getting bending moment at D, 15. Bending moment at C will be 135. It will not be different. 135 it should be. Okay. So, bending moment at D is minus 10. So, we have to once verify these calculations. Okay. But the procedure is that by finding shear force values and bending moment values at different points and plotting them. Okay. So, bending moment at B is minus 10. We are getting at one point minus 10. Let us take it as minus 10. So, it is a parabolic variation. We are not drawing it to the scale. If you draw it to the scale, you will be getting exact diagram. Okay. It's only rough sketch. Okay. That's how we proceed. Okay. For drawing shear force and bending moment diagrams. And once we find this, there is one more step, one more thing to be done to find maximum bending moment values. For getting that maximum bending moment values, we equate this equation, the derivative of this dm by dx to 0. This is the condition for maximum bending moment or minimum bending moment. Okay? Yeah, by equating this to 0, dm by dx, we will get x value where bending moment is magazine. Okay, that we'll see later. For one more example, we'll see that. For now, let us stop at this point. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.